Hello, my name is Sobhi Barg. I am an assistant professor at Mid Sweden University. My work is about the design of DC inductor, and my presentation of today is entitled DC inductor design using the unique air gap equation. I have organized my talk as follow. I will start by discussing some existing issues that are related to the calculation of the air gap used or presented in the literature. Then I will present and introduce the new equation, which is derived from Ampere's law. In the third part, I will discuss the principle of the proposed method to design the DC inductor. I will follow this with some example to understand the relationship between the different variables, and I will finish with the conclusion. The common existing equation to calculate the air gap that I have found in the literature are given by equation number 1 and equation number 2. To remind for equation number 1, you can obtain this by equating the equation used for the energy in its electrical form to the equation used for the energy in its magnetic form for the inductor. And if you equate both equations, then you can get this equation. You have to mention that R here is the reluctance of your magnetic core, and L is the inductance, A is the cross section, Lc is the core length, and mu r is the relative permeability of your magnetic material. For equation number 2, it characterizes the magnetic energy that can be stored in DC inductor, and as you can see, it is function of the cross section and the air gap, and this is because all the energy it will be stored in the air gap and not in the magnetic material because of its high and infinite relative permeability. I have some issues to raise up for these equations. So first, as you can see from equation number 1, that the air gap is inversely proportional to the cross section. That's very basic understanding from these mathematical equations. For the same thing, in the equation number 2, if you try to fix the magnetic energy E, then if you change the cross section A, then you need to change inversely the air gap to keep the energy constant, and hence we can understand that the cross section is inversely proportional to the air gap. However, this is not correct because these equations, they are derived equation. They are not the fundamental equation, and they include redundant variables here. So I have to say that the calculation of the air gap using this equation are not accurate. And if you use this equation to optimize your inductance, then you will get also inaccurate results. And if you understand that the air gap is inversely proportional to the cross section, this is not correct and it is completely wrong. It's the same thing for equation number 2. Now I will introduce the correct equation to calculate the air gap. So it is called the equation, I called it unique air gap equation, and that's because it's derived from Ampere's law. Ampere's law, it is a fundamental law in electromagnetism theory. And if you apply Ampere's law to the inductor, we can get the following. So it's the number of turns here to the right side times the current, it's equal to the magnetic field times the length. And as we have two mediums in the inductor, the air gap, which the air is the first medium and the magnetic material is the second medium, then Ampere's law is written by equation number 1. And if we replace the magnetic field by the magnetic flux density, we get equation number 2. And then finally and simply you can derive the air gap equation given here in the bottom side of this slide. So now I will introduce the proposed method to design your inductor. So the proposed method, it consists to solve for the number of turns and the air gap this system of two equations. The first equation is called the unique air gap equation, and the second term in this equation, it can be neglected because the relative permeability is a little high and infinite. And the second equation is called the reluctance model, and it's combination of Faraday's law and Ampere's law. So the solution for this system of equation is first the air gap, which is the same equation of the system, and second the number of turns is given by equation number 3, and that's exactly Faraday's law. As you can see from Faraday's law, that the cross-section is inversely proportional to the number of turns, and the relationship here, it's completely bijective. So the number of turns depends on the cross-section depends on the number of turns. And these two variables, they are physical variables. For the second equation or the first equation for the air gap is proportional to the number of turns. And this is an injective function. It can only go for one direction. So it means that the air gap depends on the number of turns, but it is not necessary that the number of turns, it depends on the air gap. We will see some cases for this fact. So to understand the relationship between the air gap and the cross-section, we can start from equation number 3. As you can see, the number of turns is inversely proportional to the cross-section. From equation number 1, you can also understand that the air gap is proportional to the number of turns. And the basic understanding, by combining these two equations, you will get that the air gap is inversely proportional to the cross-section. However, this is a mathematical understanding of the equation. The physical understanding of the equation is completely different, and it will show you that this one is not correct. So the right way to understand the relationship between the cross-section and the air gap is to go through equation number 2. That's the physical model of your inductance. So starting from equation number 3, that's Faraday's law. We have number of turns inversely proportional to the cross-section. Now we go to number 2, which is the physical model. You can see that the inductance is function of the number of turns squared multiplied by the cross-section and divided by the air gap. So to understand the relationship and the interaction with these two variables, we can fix the inductance. That's the efficient way to understand the relationship and how the variables are interacting. So let's fix the inductance and make a change in the cross-section. What will happen? The number of turns has to go inversely proportional to the change of the cross-section. And this according to equation number 3, which is Faraday's law. But as the inductance is function of n squared, then will be a remaining effect due to that square. And that remaining effect has to be cancelled out by a change in the air gap according to equation number 1. And then we keep the inductance constant. So what we get, the cross-section change, the change in the cross-section will be compensated by the number of turns, but you will get a remaining effect in the number of turns. That remaining effect has to be cancelled out by the air gap, and hence there is no relationship, there is no dependence between the cross-section and the air gap. To understand this interaction between these variables, we can go step by step exploring the effect of each variable. Starting from this example, let's fix these conditions and let's consider the cross-section as a variable. So what will happen now, according to the equations that we have presented in the previous slides, the number of turns will go inversely to the cross-section. However, as the number of turns changes, the air gap also, it will change by the same way. It is the change in the air gap has to be equal to the change of the number of turns. Also, mathematically, you can plot the air gap as function of the cross-section, and you will get the same plot as the number of turns as the cross-section. But that's not correct, because this is only mathematics. The physics, it says that the air gap is linearly dependent on the number of turns, and the air gap is completely independent on the cross-section, as we have seen in the previous slide. Now let's explore the effect of the relative permeability. We fix these conditions, and in this case, the cross-section is fixed. The air gap, it can be put to 0 because it is negligible. It's the core length, it can be neglected. And let's put the relative permeability as variable. In this case, we will change the magnetic material. So the air gap we get, that is it is function of the relative permeability, and that's according to the equation, the unique air gap equation. An increase in the relative permeability requires an increase in the air gap, and that's very reasonable and logic. So the air gap is non-linearly dependent on the relative permeability. However, you can see that the number of turns, it does not depend in this case on the relative permeability. The number of turns, it's only depend on the cross section that's according to Faraday's law. So the number of turns is completely independent on the relative permeability. Now, to understand this point, we will fix the air gap to 0 and calculate the required relative permeability, the required magnetic material for a given condition. In this case, I will fix the number of turns to a minimum equal to 1. I will fix the magnetic flux density and the current. So what is the required relative permeability in this case? Your magnetic material has to have a relative permeability of 237. Now, if I change the magnetic material to 2000, let's consider another material, and what we'll get, the maximum current in this case that you can handle, it will be 0.1 amps. You can see it is decreased 10 times than the previous design, and that's because the relative permeability, it is increased about 10 times. So in this case, what you have to do, you need only to increase the air gap. You don't need to change the number of turns. Now let's explore the effect of changing the inductance. Sometimes you need to change the inductance because you change the frequency in DC-DC converter. But for the same power, you need to increase the frequency and then you can decrease the inductance. That's very common in the design of DC-DC converters. So in this case, I will put the inductance as variable and I will fix all the remaining variables. So in this case, you can see that any change in the inductance, it will leads to a similar or linear change in the number of turns and in the air gap. In this case, the number of turns will change and the air gap also has to change. It has not to be constant. You need to change the air gap whenever the number of turns change, and that's according to the unique air gap equation and Ampere's law. So the air gap is linearly dependent on the number of turns, and thus per the Ampere's law. And also the number of turns is linearly dependent on the inductance. If you need to increase the inductance, you have to change the number of turns as well. But if you change the number of turns, you need also to increase the air gap. In this case, we understand that the inductance, it can only be increased linearly. You cannot increase the inductance in non-linear way. And this, according to this, to the unique air gap equation. So in this case also, we can understand that the inductance, it is size dependent, because whenever you change the number of turns, the size of the inductor or the core will change. You have to change the size as well. Let's consider this example to understand this important relationship between the number of turns and the air gap and the inductance. So in this case, I will fix the number of turns and I will see if I can change the variable. So I need to change the inductance by a factor of X. In this case, I have to change the cross section because the number of turns is constant. Now, what will happen when I change the cross section according to this equation in the bottom? If I change the cross section, of course, the magnetic flux density will change, and that's Faraday's law. And if the magnetic flux density change, then you have to change the air gap by the same factor. And if the air gap change, then the inductance will keep unchanged. You have started by changing the cross section, and that's change in the cross section A leads to change the magnetic flux density. If the magnetic flux density change, then you have to change the air gap, and then you will keep the inductance constant. You cannot change the inductance by changing the cross-section only. You have always to change the number of turns. And if you change the number of turns, then it will cancel the effect of the change of the cross-section, and finally you will conclude that the air gap, it only depends on the number of turns. So this way to change the inductance is not feasible. As a conclusion, we have to always understand that the air gap is naturally independent on the cross-section in electromagnetism. For a given current, DC current, magnetic flux density, and relative permeability, the air gap is uniquely dependent on the number of turns. You have also to remind that the inductance is always size dependent. The unique air gap equation that we have presented today is a direct application of Ampere's law. The design method using the unique air gap equation is more accurate than the area product and the core geometry coefficient methods. Design method using the unique air gap equation enable to design the winding of the DC inductor without knowing neither the magnetic core neither the core material, and this the advantage of this method compared to the area product and the core geometry coefficient.